Okay, probability. So the first thing we did when we studied probability was the counting principle. That's when you have so many options, you know, like toppings on a pizza, or what's going to go into a sandwich, or how many outfits you can make. So the way that works, you just take the numbers, the shortcut, then you multiply them together. So I have 3 shirts, 2 pants, 5 pair of shoes, multiply them together. That gives me 30 possible outfits to wear. And the reason behind that is, let's say you have a red, white, and a blue shirt. For each shirt, you have 2 pair of pants you could possibly wear. And for each pair of pants, then I have 5 different pairs of shoes that could go with that pair of pants. So in the end, that's where, when you add those all up, that's where you get your 30 possible combinations. But again, the shortcut is just counting principle, multiply them together. These are also where you get the license problems. So you have a 7-digit license plate, and we want to know how many possible combinations, 1, 2, 3, 4, 5, 6, 7, are possible if you may not have a 0 or a 1 allowed in the first place. Well, there are 10 digits to choose from, so if I can't have a 0 or a 1, that limits me to only 8 choices for the first place. Now when I go to the second place, I'm not allowed to use the number that I'd already chosen, so I only have 9 to choose from. So that leaves me with 9, and then it's going to go down by 1 for each time, since I'm not allowed to have any repeats. And when you multiply that all together, that's the counting principle, you get 483,840 possible combinations. Then we had permutations and combinations. Permutations is where order matters. You're taking something from a group, and the set of 3 that you choose is going to be ordered in such a way that each selection is different. President, vice president, secretary, first place, second place, third place. There's somehow some sort of a category chosen so that order matters. So the permutation is the number of things you're choosing from, that's the n factorial, over, or the group number over the group number minus what you're actually choosing. So for instance, how many ways can a president, vice president, and secretary be chosen from a group of 20 is, of those 20, you are going to permute 3 of them. So that would be 20 factorial over 20 minus 3 factorial. That's going to be 20 factorial over 17. So that's like 20 times 19 times 18. As soon as you get to 17, that's going to cancel, and you're just multiplying 20 times 19 times 18, which is 6,840 ways you could choose a president, vice president, and secretary. In how many ways can you rearrange the letters in the word abracadabra? So this is the same idea. You're going to count up how many letters there are. So there's 11 letters in abracadabra, but because we have repeats and we don't want to count the letter A multiple times since it's the same letter, we're going to divide by those repeats. So 1, 2, 3, 4, 5 of those. So 5 factorial. Then we also have 2 B's, so we're going to divide by the 2 factorial for the B's. And then we also have 2 R's, so we divide by the 2 factorial for the R's. And when you then rearrange that, so that's going to be 11 times 10 times 9 times 8 times 7 times 6. As we get down, then if I were to go to 5 factorial on down, that would cancel with the 5 factorial on down. The 2, well, the 2 could go into this 3 times. The other 2 could go into your 8 4 times. Multiplying what's left is going to give you 1,386,990 ways to rearrange the word abracadabra. So have fun with that. Alright, also then we had combinations. Combinations is when order doesn't matter. So if I'm choosing a group of 3 people, it doesn't matter whether it's Sally, Susan, and Sam, or Sam, Susan, and Sally. It's the same group of 3 people. So you're actually going to have a smaller combination possible. So the way this works is when and I think combinations work best when you're choosing something from, you have several groups and you're choosing a subset from those groups. So you have a class of 12 boys and 15 girls, and you want to know how many different ways can a committee of 3 boys and 3 girls be formed. Now again, this isn't probability, this is how many ways we can do this. So of the 12 boys, we are going to choose 3 of them, and so times of the 15 girls, we're going to choose 3 of them. And you can either go to your calculator and do that, or these are going to be, you're going to have the 12 factorial over 12 minus 3, which is 9 factorial, times 3 factorial, and that will get multiplied by 15 factorial over 15 minus 3, which is 12 factorial, times 3 factorial. So I'm running out of room, so we're going to make this a little smaller. So if we were to work this out, 12 factorial would be 12 times 10, sorry, missed it, 11 times 10. As soon as I get to the 9, that's going to cancel with this 9 factorial. 3 factorial is the same thing as 6, so 6 would cancel with the 12 to be a 2. So basically I'm going to have here 22 times 10, which is 220. And then we have our 15 factorial, so 15 times 14 times 13 times, as soon as I hit 12, that's going to cancel with this 12 factorial. And once again, the 3 factorial is the same thing as 6. Okay, so 6 doesn't go into any of these evenly, but we can, 6, let's see, 3 goes into it twice, so 3 goes into this 5 times. 2 goes into 14 7 times. So we end up here with 35 times 13, which is 455, and that gets multiplied by our 220. Oh, that's a really interesting number. That's going to give us 100,000 and 100 different ways that those 3 boys and 3 girls can be chosen. So up to now we're just looking at different ways and different combinations that things can happen. Now we get to probability. Probability is always going to be a fraction, and it is always going to be a number between, when you have your probability of an event, between 0, which means it's definitely not going to happen, and 1, which is 100% certain to happen. It usually falls somewhere in between those. So the probability of an event is their favorable outcomes, what you're looking for, divided by the total possible outcomes. When you are multiplying by probabilities, that's going to be and. So the probability of A and B happening is probability of A times the probability of B. And that also happens when it's the probability of A then B, something happening right after something else. So a lot of times if you're, picking marbles from a ball, marbles from a bowl, then if you are not replacing something, the probability of picking the next one is going to be dependent on what previously happened, and so your sample space will have to go down as well. We're going to do some examples in the next slide. When you're adding probabilities, that's going to be your OR. So the probability of rolling a 5 or a 3, so you actually have a bigger probability because you're accepting more options, and that's if it's mutually exclusive. When you have an overlap, say for instance the probability of rolling an even number or a 2, you have to then take into account that the 2 is also even and you don't want to count it twice, so in that case you would have to subtract how many items are in the intersection of the 2 possibilities. Okay, so let's take a look at some of those examples. Okay, a jar contains 3 red, 4 green, 5 orange marbles. So we have a total here of 12 marbles in a jar. And we are going to draw 3 of them without replacement, and we want to know what is the probability of all of them being green. Well, I have 4 green, so of the 4 I'm going to choose 3 of them and nothing else, and that's so that's the favorable outcome I have. I have a favorable sample space and I want to choose 3 of them, but my total sample space is 12 and I'm still only choosing 3 of them. So then when you divide that, well, 4 choose 3 is 4, and then you have your 12 choose 3 is 220. And that is going to reduce to, I believe, 1 over 55. Now what if it's the probability of 2 red and 1 orange? Okay, well, we look at our red sample space. I have 3 that I can choose 2 of. That's what I'm looking for. That's my favorable. And of the 5 orange, so it's times, because it's and, times 5, I'm going to choose 1. So notice that gives me my total of 3. And that will be divided by my 12 choose 3. So 12 choose 3 we know comes out to be 220. And 5 choose 1, I believe, is going to be just, I'm thinking it's going to be 5. It is. And your 3 choose 2 is going to be 3. So we have 15 divided by 220, which is going to give you 3 over 44. Okay, then we have 2 cards are drawn from a standard deck of cards, that's what that means, with no replacement. So that means each time you pull a card, the sample space is going to go down. So the probability of a jack and then a jack, well, we have, let me see, we have 4 jacks, right? So, so you have 4 jacks. So that's 4 out of the 52 cards. That's the probability for the first draw. The next draw, since we've already chosen a jack, I only have 3 left, and there's only 51 cards left. So that's going to give me 12 divided by 52 times 51, and as a fraction, that's going to give you 1 out of 221. Then what's the probability of 2 diamonds? Kind of the same idea here. So there are 13 diamonds in a suit, so 13 out of the 52. But once we've chosen one, then there's one less to choose from. So this is going to give me 221 on the bottom, and 13 times 12 on top. And so 156 divided by 221 is going to be 12 out of 17. Okay, now if we allow replacement, what is the probability of, so well, in this it doesn't even make sense. We don't even need the allow replacement because it's an or situation. What is the probability of picking, so we're only choosing 1 card now, I should have put that in here. Choosing 1 card, the probability of a king or a red card. So there are 4 kings, so that's 4 out of 52. Or, so that's plus, a red card, there are 26, half the decks, because of the diamonds and the hearts, 26 out of 52. But there are 2 kings that are red cards, so we have to subtract those 2 kings. So in the end, and it's good not to reduce until the end, so you keep the same common denominator going. So if 30 take away 2 is 28, so that's going to give me 28 out of 52. And then if you reduce that, that gives you 7/13. And what is the probability of an ace or a face card? An ace or a face. An ace, there are going to be 4 aces, so that's 4 out of 52. Or, that's plus, a face card. So there's jack, queen, king in each suit, and there's 4 suits, so that's going to be 12 possible face cards. And there are no face cards that are also ace cards, so this comes to be 16 out of 52, and then we can just reduce that, and that is going to give you 4 out of 13. Okay? Okay, lastly, we have our mean, median, mode, our measures of central tendency is what these are called, and your standard deviation, which tells you how far away from the mean your set of data fall. So it's a measure of variance. So the mean is something that we've done many times. When you're finding a midpoint, you're finding an average of 2 coordinates. So that's when you sum up all of your data and then divide by the number of data items that you have. The median is when you put everything in order from smallest to greatest, or greatest to smallest, however order you want, and then you go from each end to find the number that is right smack in the middle. The mode is the most, so the most frequent data item in a list. And the standard deviation is a massively large formula. But it's not too bad if you are organized about it. Okay, so your first step is to find the mean of your data, and that's what this X bar is. So we're going to do it on this small set of numbers down here. So to find the mean, I'm going to add these numbers together. And what I'm going to do is give myself a little bit of room to work over here. Okay, so we're going to find the mean of our data. So the way you find your mean is you add your data together. So we have 3 plus 3 plus 4 plus 6 plus 9. So that's 10 plus 6, 16 plus 9 is going to be 25. And that's going to be, I have 5 numbers. So I'm going to divide that by 5. So I have 25 divided by 5. That was fortuitous because I just made those numbers up. So my mean is 5. Okay, so that's nice. Now what we're going to do is we're going to make a list. And we are going to take our mean and we're going to subtract from it each of these data points. Okay, now because I have several 3's, I only need to do it once and then multiply that by 2. So I have 5 minus 3, and 5 minus 3 squared is what we're going to look at. But because I have 2 of those, I'm going to do it twice. And then we're going to add that to 5, my mean, minus the next number, which is 4. And we're going to square that. And then we're going to go 5 minus 6, and we're going to square that. The order doesn't matter how you subtract them. Notice in the formula it has x3 minus x bar minus x3. It really doesn't matter because you're going to square the result, so everything comes out positive. And then I'm going to take my 5 minus the 9, and I'm going to square that. So looking at the result, I have 2 squared is 4. 4 times 2 is 8. 1 squared is 1. 1 squared is 1. 4 squared is 16. And you add those numbers together. So I'm going to have 24, 25, 26. And 26 divided by 5. And then we're going to take the square root of that. So that undoes the squaring that we did. So we have 26 divided by 5, which is 5.2. And the square root of 5.2 is going to give me 2.28. So turns out that sigma is going to be 2.28. So that's telling me, what percentage of my data in general, if this were a normal distributed curve, will fall from the mean, will fall away from the mean. So if they ask you what is the standard deviation, you would say it's 2.28.